Good morning. Welcome to Krishna's class. Now, in this talk, we take up what are called semicontinuous. Let's start with the definition straight away. We define what is called lower semiconductor. Let F be a real valued, real or extended. Let F be a real value or extended real valued function. Defined on a topological space now tau is the topology. Now, if this is the definition, the set of all x, the property that fx is greater than alpha, which is the same as f inverse of alpha infinity. Now, if we are using extended real value, then we take plus infinity and minus infinity also in R. So, you will have R star equal to or L infinity and plus infinity. This is the extended real valued function. So, this is the same as this is open for alpha, then f is said to be lower semiconductor. Then f is said to be. So the condition that you have is this. This is true for every alpha. Similarly, you have upper continuity, upper semi. Once again, f real or extended real valued functions on x. That's x star. Now, if the set of all x for which yes, which is the same as inverse of minus infinity. Now, this will be small bracket if you are talking about real value. Is open for every then f is set to upper semicontinuous. Let's just examine these statements. Okay, and of course, a real function said to be continuous if it is both lower and upper so continuity is what happens, it is upper continuous and lower semicontinuous. Both these properties are satisfied. Now we'll look at some examples. I mean, that's the better way to understand this. Now, in fact, I want to make some remarks, but possibly I postpone it until I get some examples. So we'll look at an example. Right. We look at examples which are not either lower semicontinuous or upper semicontinuous. A very simple example where you can visualize what is going on easily is this. Take x to be equal to r. Now, you take a belonging to r. Now, define fx to be equal to the characteristic function of the closed set Now, you know that this is a discontinuous function. In fact, one can easily draw the graph of it. It has a discontinuity at a. So, the graph of the function is the following. Suppose this is A, not necessarily positive. Okay? But what I have done is to set the function to 1, and 0 up to the point A. At A, the function is equal to 1. Therefore, clearly you can see that minus equal of equal to 0, which is not equal to f. So the discontinuity is at this point. But then f is continuous from above, but discontinuous below. Why it is? Because you have limit extending to A plus equal to 1, which is equal to the function value of. So it is discontinuous from below, but continuous from above. This is the situation. Okay, so you call it the upper semiconductors, or in other words, F is upper semiconductor. And not here we are using only elementary calculus. Okay. Now we will take up the equivalent statement of this in terms of this. What happens to, or what is F inverse of let us work on this. Okay. Now you see that if alpha is here, then F inverse of minus infinity alpha would consist of the range, that is 1 and 0. Okay. So 1 and 0. So see, if your alpha is somewhere here, then you take the F inverse of minus infinity alpha, that is this portion. Okay, and what is that? That consists of the whole space. Okay, then this is equal to the whole of R alpha is greater than. Okay, and in fact, even if alpha is okay, what happens to this? So what happens if alpha is equal to 1? Suppose alpha is equal to 1. Then this is going to be what? Okay. See, this portion is excluded, so it is only this part comes. So it is going to be minus infinity a. And this is open, this is also open, and this is equal to from 0 to 1. In fact, you can write this, modify this and write zero. Now what happens to this if alpha is equal to 0? If alpha is equal to 0, then you get again the same set. So this is equal to, or I can modify this now. And then what happens? This is equal to, this is empty if alpha is therefore you see that in all these situations they are all open sets. So F inverse of therefore you see that F inverse of what is the consequence? Therefore F is upper matrix. Is F lower semicontinuous? Now we shall once again go for the analysis. So here what you have to look at is the following. So consider F inverse of alpha now what is this? You see that this is going to be empty whenever alpha is greater than greater than but if alpha is equal to 1, Now let us take at this. What happens? What happens if alpha is equal to 1? If alpha is equal to 1, then this is going to be, so it is going to be from here to here. See that 1 does not belong to that. Therefore, this is. Now F inverse of if you take the case where 1 less than, sorry, less than, then what happens? Then you see that clearly this is going to be a to infinity. A to infinity. Now this is not open. Now this is the important. This is true for all this. In fact, just that is enough to conclude that. And you can analyze likewise F inverse of in fact, this is also true. In fact, this is equal to the whole of R if alpha is. So you see, what happens is for every alpha lying between 0 and 1, see, this is going to be not open. This is important. Therefore, the function dot not oversight. Therefore, it's a, sorry, yeah, the function is upper semiconductors but not lower semiconductors. Okay. Now suppose you take likewise, one can analyze chi of the characteristic function of A infinity, and this is equal to 1 whenever x belongs to A infinity and equal to 0 now this function is continuous from this function. What is the property? The property is that this at this point now it is going to be 0. So it's not upper semiconductor. It's not continuous from it. but continuous from below. Now this is expressed by saying that it is lower semicontinuous but not upper semicontinuous. But not upper semicontinuous. I am not repeating the argument by writing down the F inverse of alpha infinity for every or yeah, F inverse of uh, F inverse of alpha infinity and F inverse of minus infinity alpha in this case, because they can be done exactly the same way, but taking proper care when alpha takes the value 1 or 0. Okay. So this is something that you can see. I am not going into the now you see that F is continuous if it is both lower and upper so you can easily see this, that is F inverse of that is here it is. That is when both these conditions are satisfied, then you call it continuous. Okay. So we are going to the final details. Now let us analyze this with the measurability criteria that we had earlier. Okay, let us just read. See, you have X tau. This is a topological space. Let a sigma algebra M be something that contains tau. Then of course what you can easily see is that M consists of all closed sets because complement of open sets. If open sets are all measurable, then closed sets are all. Then the class of measurable sets are closed under countable unions and countable intersections. So it's a huge class of sets that you can build. In fact, you see, you have the Borel class of sigma algebra, which is the smallest collection of open sets which contains sum. Okay. Now you recall the following definition. Let me just, because I think this comparison is something which you should. Now we say that F is measurable. Okay, F from X to F is measurable if and F inverse of say alpha infinity is measurement. Which is equivalently if and only if F inverse of minus infinity alpha is measurable. Of course, for okay, compare this with the semi-continuity criteria. So here, you see, these two statements are equivalent. That if it is measurable, if F inverse of alpha infinity is measurable, then F inverse of minus infinity alpha is also measurable. Okay. In fact, this is because if open sets are in M, then closed sets are also in M. Whereas for a continuous function, the condition that you have is this: F inverse of F is continuous if F inverse of any open set O open is open. O is open in okay, right? Therefore, what happens in the case of continuity? The case of continuity, one part of this is true, you cannot say it is continuous. Only if both these are simultaneously true, then only you can say it is continuous. Because one does not imply the other. Or in other words, the statement I have made here equivalently is not valid anymore. Okay? A lower semi-continuous function may not be upper semi-continuous, as we have seen the examples. Whereas you see that all lower, with this sigma algebra, that is sigma algebra containing all open sets, you see that all lower semi-continuous functions are measurable, all upper semi-continuous functions are measurable. Okay, needless to say, all continuous functions are measurable. Now, this is one reason why we choose a sigma algebra which contains the open sets. Whenever you see you are working on a topological space, okay, there are situations in measure theory where you do not have any topology defined on X, or you don't need to have any topology on X, and then you can develop a theory on that. But certainly this is more advantageous because if you want to do analysis, then you come across continuous functions, and you see that the definition of measurability assures that all continuous functions are measurable. Whereas, and so also it assures that all semi-continuous functions are measurable, whether it is lower semi-continuous or upper semi-continuous. Okay, therefore, it's a huge class of measurable functions. But lower semi-continuous, if a function is lower semi-continuous function, then you cannot say it need not be a upper semi-continuous function, nor a upper semi-continuous function be a lower semi-continuous function. Now we make some general things which you can easily prove. Okay. Now note that one characteristic functions of open sets are lower semi-continuous. Two characteristic functions of closed sets are upper semi. Upper semi-continuous. Now that you can easily check this in the case of our examples. Okay. Now when we defined these functions, we have found that chi of infinity. Now this was lower semi-continuous because this is the characteristic function of an open set, whereas this is the characteristic function of a closed set. So this is lower, this is up. That's what we have. Okay, this is the example. Now one has to carefully analyze this with an improvisation when you work in a general topological space. Okay, because here we have analyzed from R to R, but now we are going to analyze from a general what you call topological space. In that case, some more careful look at this is required, and I leave it as a exercise. It's worthwhile sitting for some time and taking lessons from this particular example and analyzing them and using the properties of an open set and a closed set. The open set and making use of the concept of open set and closed set in a topological space. Now the third property is that the supremum of lower semicontinuous function is lower semicontinuous. For the infimum of upper semicontinuous functions is upper semicontinuous. Now one has to be careful. Now you see, you recall how to build the proof for this. I mean, it's quite similar to how we handled the situation in the case of measurable functions, measurable real valued functions. There we said that if a sequence Fn is measurable, then the supremum of this sequence is measurable, the infimum of this sequence is measurable. That is because you have got this, when you take the measurable or take the sigma algebra, it consists of both open sets and closed sets. Whereas here it is not there, we are working with tau as the collection of open sets, and only with reference to tau you are making all these definitions. Okay, so that's a remark. And the proof can be done exactly in the same way. We proved the supremum and infimum of measurable sets are measurable. Okay? Exactly following the track, but carefully separating the two cases, namely the characteristic functions of open sets, or what you call the supremum of lower semicontinuous functions, and infimum of upper semicontinuous functions. Here it is supremum of lower semicontinuous functions. We are not talking about the infimum of lower semicontinuous functions, whereas we are talking about the infimum of upper semicontinuous functions and not the supremum of upper semicontinuous functions. Okay, so that's and you can construct some examples and get some insight into what this concept is. Just need some little bit of soiling your hands. Okay. Now we make some definitions. The support of a complex value function F on a topological space system is closure of the set on which the function does not vanish. That is, we take this. This is what we call so this is the definition of now we are interested in what are called functions with compacts. The definition is obvious. Those functions which have their support a compact subset of X. Okay. So such functions we designate by CCX. Okay. A collection of all continuous functions. Here, remember in our definition, okay. Yeah. Now here we are taking F to be continuous. The collection of all continuous functions with compacts. That is F continuous such that the by definition itself this is closed, but you don't know whether it is compact or not. Okay. Right? Okay, right. So this is the condition that are designated by C, designating continuity, small c down, designating compactness. So this is, okay, so it is called CCX. Okay. Now, so CCX continuous and compact. Now, what are the properties of this collection of functions? They have some nice structural properties, nice algebraic structural properties, like these functions form a vector space. Is a vector space over R, over C, because we are talking about complex value positions. This C is different from this. Okay. This is because the reason is support of F plus G is contained in G. F continuous implies plus. So also alpha F is continuous. Needless to say that alpha F has the same support as that of so these properties do ensure that this is a vector space. Of course, here we also need that finite union of compact sets is compact. Now, this is the sort of tools that you have to use, or topological results that you could use to prove that CCX is a space over C. Okay. Now let us prove a theorem which is a consequence of this definition. Suppose X and Y are topological spaces. It's a general theorem. This theorem essentially deals with the interaction of continuous functions with compactness. Okay, make a remark of this. Let be continuous. Continuous. Then what we can say is that F maps compact sets into J is compact. Then Fk, image of K under F is compact. This is a useful tool which we shall need someday. So it's very easy to prove this also. That is compact sets are mapped. Compact sets by continuous functions. And this is the remark I made, that this theorem essentially deals with the interaction between continuous functions, or what continuous functions do on compact sets. So that's a useful result. So we shall prove this. Proving is very simple. So see, you have x here, y here, both are topological spaces. This is K, which is compact. This is K. So K compact, that's Fk is both are topological. We'll prove this. So what we do to prove, see, our objective is to prove that Fk is compact. So let me take an open cover for this, and then we show that it has a finite subcover. Let here there are two facts given. One, F is continuous, therefore the inverse image of any open set is open. Therefore, F inverse of B alpha is open for every alpha. Secondly, since B alpha is an open cover for Fk, you see that F inverse of B alpha is an open cover for K in X. I mean, that is quite easy. Okay, so that's a straightforward result. Since K is compact, there exists that Fk is P alpha. That means this becomes this collection of open sets is a open cover for K. Since K is compact, there is a finite subcover, and that finite subcover becomes. And this in turn implies F of K is contained in that means we have proved that if B alpha is a open cover for Fk, then it has a finite subcover. Therefore, that's a simple result. Okay, I think I'll just give a immediate corollary which we shall see sometimes in that form. If we are talking about a complex value function, the complex value function f continuous and k then f of k is compact. And this is true so every continuous function, continuous complex valued function f on a topological space is the property that it maps compact sets into compact sets. Okay. So thank you very much. Let me conclude today's talk at this stage.